Thank you. Welcome to our regular Monday seminar. And today it's my pleasure to welcome Matyáš Křišťan, and he will be a talk on configuration under some generalized.
Thank you for the introduction. I will be presenting my joint work with Reconfiguration from Austria. And first, let me show what's the problem that we will look at. So, in our problem, we are given a graph and two solutions to some graph problems, such as vertex cover, for example. And our task is to reconfigure one solution into the other. And we will be given some rule, like how to change one solution, usually some small change. And all the intermediate solutions also has to be vertex cover or solve this problem. So we will look at a few graph problems, vertex cover, independent set, and dominating set. And we will look at the generalization of a rule that is already very studied, called token jumping. I will show an example how it works. So in our generalization, we have two parameters for the rule. One is how many tokens at once can jump, and the second parameter is to which distance. So in this example, we would have this graph and this red vertex cover and this vertex cover BT. And our task would be to find a sequence of moves that satisfy some given rule, such that we reach one from the other. So, for example, we could take this token and move it to the right. Then we could move along these arrows, reaching this configuration. So we needed to move at most 3 tokens at once and only to distance 1. So this would be valid under rule 3.1. We could also, for example, start here, and to reach this, just take this token and have it jump to distance 3, and we are right there. So this would be another sequence, but it would be under 1-3 token jumping. So we will try to search for some minimal rule that will guarantee us that we can reconfigure any solution into any other. And first, there is an easy lower bound that we will need, in some instances, every token to move. If we look at cycles, then for vertex cover and independent set, there are only 2 disjoint minimum solutions for vertex cover and 2 disjoint maximum solutions for independent set. And to move one from the other, there is no other intermediate solution that we can use. So we have to move directly between them, and therefore we have to move every token at once. Same thing is for dominating set, except there are 3 disjoint solutions. So right away we can see we'll have to allow every token to move if we want this guarantee. And we can look at the next parameter, like the distance to which the tokens can jump. So I will show these results in what will follow. And for vertex cover, we will show like the time bound. And for each case where there is no, we also have some example where like it is not possible to configure under the rule. Because there would be some gap. In case of dominating set and independent set, we can look at like more detailed rule. So we will have like these 2 parameters, K prime and D, and we will always allow all tokens to move at once, and we will see what else do we need additionally. So this table shows that to guarantee that dominating sets can be reconfigured, we also have to allow at least K minus 2 tokens move to distance 2, and for independent set, we need to at least 1 token allow to move to distance at least 3. And this is tight in the sense that we also have, like for this red part, we have counter examples where instances cannot be reconfigured. So let's first look at the vertex cover. So our task will be given to vertex cover, find a reconfiguration sequence between them. We will show this by an algorithm that will produce the reconfiguration sequence. And the first step is to take these 2 vertex cover we were given on input, and we will use it to compute another vertex cover, which can be reached from the other 2 in a single move. So first, we'll construct this bipartite graph B, with one side is 1 vertex cover, the other is the other vertex cover. And we connect 2 vertices by an edge if they are within distance 1. And first, we will have to put some candidate vertex cover, which could be the intermediate one. We can big example for a copper of Vs or Vt. And now we will check if there is a perfect matching between them. If there is a perfect matching, that is the move we can use to move from one or the other. If there is no perfect matching, then we can use Hall's theorem. Hall's theorem says that if we want a matching that will saturate this Vn part, so if such matching doesn't exist, this must be because there is a violator, a set of edges, whose neighborhood is smaller than the set. So, for example, these two cannot be, these three cannot be matched to these. Yeah, I hope this is, yeah. So, okay. So we will take the Hell violator, and we can use this smaller set and replace this bigger set with it. And by the construction of the bipartite graph, you can see that these are the exactly all edges that are covered by these vertices and by these vertices. So it's safe to remove those and replace them by these. So in this step, we will obtain a new vertex cover, which is smaller. And in this case, we will obtain the matching. So we'll be able to move some tokens from Vs to Vm. So we can repeat this process. If we wouldn't have a matching with this vertex cover, we can do that again. And anytime that the whole condition is violated, we can decrease the size of the vertex cover. So after at most n steps, we will have to reach vertex cover that works. We will do this from both Vs and Vt. So if one of them doesn't have the matching, that gives us a chance to decrease the vertex cover. So this will give us a vertex cover that has a move from both of them, Vs and Vt both. So if we obtain this common vertex cover, we have to resolve one possible small issue. It could happen that the resulting configuration would be a set of tokens. There could be two tokens on vertex, but we can just add weights to the edges and pick minimum cost matching, and this turns out that it works. We will always obtain a matching which will not use a vertex twice. So using this technique, we have reduced to this case. We have started with this Vs and Vt, and we can move to configuration from Vs, and we can also use the move in reverse, of course. So we apply the first and last move. And now we have to reconfigure between V'S and V'T, but we already have a vertex cover that is in intersection of them both. So we will do that in a way that the green vertices, the green vertex cover will always be occupied, and we can do that quite simply. We can just take one token and move them one by one. For example, move this one to above. If there are no tokens in the way, then there is no problem. If there would be some tokens in the way, then we can just move the whole line of tokens that block it, and that will result in a configuration that looks like jumping over those tokens. So this algorithm gives us the theorem that for any two vertex covers, there is a reconfiguration sequence under K1 token jumping, and it will use at most unsquared moves. So let's look now at dominating set. So in the previous argument, we never used the fact that the edges would contain only two vertices. We can use the same argument also on hypergraphs. And for dominating set, you can start with formulation using a hypergraph which has the same vertices as the original graph, and edges are the close neighborhoods of the original graph. And it is easy to see that vertex cover in the hypergraph are exactly the dominating sets in the original graph. And also a move in the hypergraph along an edge that corresponds to a move to distance at most 2 in the original graph. So just using this formulation using a hypergraph, we get that the dominating sets can be reconfigured by moving two K tokens at once to distance at most 2. Here is a corresponding Clover bound, which turns out to be the worst case. So we can extend this graph to any size by taking a copy of Q1 and editing it, identifying the vertices A and B. And the best possible move here is here use move of distance 1, here also distance 1, but all the remaining pairs of vertices will need a move of distance 2. So this graph will need at least k minus 2 tokens to move to distance 2. And we will show that actually we can have an algorithm that will use this reconfiguration rule. So how to go from the k2 token jumping to the just k minus 2 and 2. So the only part we have to fix is how to move into the common dominating set. We will use the same approach. Using the bipartite matching, we will find a common dominating set. And there is only a problem if we have to use k minus 1 or k jumps to distance 2. So we need to just resolve some 2 moves and make it so that they are to distance 1 or less. So first observation is that for 2 dominating sets, if we pick vertex from 1, then we can always find in the other dominating set a vertex that's at distance at most 1. So we will use that in the following algorithm. So suppose this is one dominating set and the other, and the red edges are the matching along which we want to move. And suppose that there is k minus 1 or k of them to distance 2. So first we pick an edge which is on distance 2. So by the previous observation, we know that there has to be an edge which corresponds to distance 1. We will try to follow it and go to the other endpoint of that edge and do that again. So it may happen that the edge of distance 1 that we would want to use is actually the one used in matching. If that happens, that's okay, and we will continue in the process starting from the same original edge, but from the other vertex. So we add these edges once again, and now it cannot happen that we would again find a different edge of this kind, because there will be 2 edges in the matching of distance at most 1, which we assumed is not the case. So eventually we will have to reach some vertex which we have already visited, and this will yield us a cycle which alternates the edges of the matching and edges of distance 1. Now we can swap in our matching these along this cycle basically, and we will exchange 2 edges in the matching by 2 edges of distance at most 1, or at least, because it's a bipartite graph. We will have a cycle of size at least 4. So in the switch we will exchange at least 2 edges. So this is the move that we wanted. We know that now it uses at most k minus 2 jumps to distance 2. And the rest of the algorithm is the same, and we just move tokens one by one. So this gives us the following theorem that basically for dominating sets, this rule is optimal, and the example that I showed shows that any weaker rule wouldn't work. If we decrease like any of these numbers, then that would be a counterexample. So now let's take a look at independent set. So for independent set, we have 2 lower bounds. One was the cycles one, which shows that we have to move everyone. This 3 shows that in some instances we need to move distance at least 3. Because if we start with this red independent set in the leaves and the blue square independent set in the leaves, then what we can do is only just take 1 token and we want to move it to the other set of leaves. But that has to be done over distance 3. Otherwise, the intermediate configuration is not an independent set. So we'll aim for an algorithm that will use this rule. So first observation is, if we could take the initial independent sets and move them into some common maximal independent set, then we are okay. At least using the 1-3 rule. What we can do at that point, we can just try to reconfigure the tokens one by one. We'll pick them, imagine there is some path along them. If there is no token blocking them, then we can jump only in the vertices of the maximal independent set, and we will do a part of the reconfiguration. If there are some tokens blocking us, then we can just pick the last blocking token and move to the goal. So this part is not that hard. So now our task will be to compute some maximal independent set given the 2 independent set, such that we can move into it from both. So again, we can use a similar argument using Ross theorem. So we want to saturate the vertices of IS. we cannot do that. But there is again a set that is larger than its neighborhood. So again, the argument is the same. So these are exactly the edges that are incident to these two sets of vertices. So if we remove this red set and replace it with this blue one, we will again obtain an independent set that is larger. And we will do that for the two independent sets at the same time. The matching has to be there for both of them. If one of them doesn't have the matching, we again can increase the independent set. So after some n number of steps, we will have the set that has matching to both. So now that we have that, we can move some of these tokens into the A star and use the previous argument to reconfigure them. So this is same kind of theorem that for independent sets, this kind of rule is optimal. Otherwise, we have counterexamples. So we've also looked at complexity, like the probability natural rule, where we can just move each token at the same time to distance at most one. And for vertex cover, we already have the result that the sequence always exists, so that's easy. We show that it's NP-complete to decide if at most L moves suffice, and for the other two problems, it's p-space complete. So one observation is that if just deciding if two solutions are reachable is p-space complete, that can at most start asking some distance is p-space complete, because we could ask for distance 2 to the n, and that would give us the solution to any sequence. So for vertex cover, there is a simple reduction. So we will reduce from a regular vertex cover problem. We are given a graph G, and we ask if it has a vertex cover of size at most k. So first we will take this gadget and add n-2 copies of it. And we will take the vertex x and connect it with all edges of G. And now, depending on whether G has a vertex cover of size k or not, we will need either 2 or 3 moves in the reconfiguration sequence. You want to move from these red circles to the state where they are on the blue squares. So what we can do always is like have one token at a time, or just these two tokens like move at the same time to reach this configuration using 3 moves. Now, if G can borrow some token, we can start a move here. We can have a token move from G and immediately have this token move here. And in the next step, we have a token move here, and this token is returned back to G where it was originally. And here we can finish the move. So if G can, to each gadget, lend some token, then we need just 2 moves. But for that to work, this has to happen in all of the n-k top copies at the same time. So G has to give up those a-k tokens at the same time, and therefore it must have a vertex cover at least k for this sequence to work. So this shows that it's NP-complete even if S is fixed. For the other problems, it's not too difficult to show the hardness. For independent set, it follows quickly from already known result by Belmuta that in a similar setting in token sliding, it's p-space complete to decide that we can reconfigure one independent set into the other. And that's even when restricted on split graphs. The split graphs are graphs which can be partitioned into an independent set and a clique. So every move has to happen through the clique. So it's not that hard to show that at most 2 moves can happen at the same time, one going into the clique, one out of the clique. And this can be split into 2 moves that are in sequence. So these 2 reconfiguration rules are equivalent on split graphs, and so it's p-space complete as well. And for dominating sets, we can also show another reduction, this time from reconfiguring vertex cover under token jumping, just taking one token at a time and moving it. And we can use a similar construction that's used in the standard reduction of vertex cover to dominating set. We will have one set of vertices which corresponds to vertices of the original graph. We will have a set of vertices for each edge and n copies for each. and we have some extra vertex x that's connected to every v and some extra vertex y. And now in the original problem, we are allowed to take one vertex, take one token and move it anywhere in the graph. So in this construction, what we can do is just take one token and move it through x. So x always has to be occupied, and no other moves than these kinds of are shown to make sense. So this problem is also p-space complete. Okay. So that's everything from me. So just to summarize the results. The main result is that vertex cover, when reconfiguring by taking the tokens and moving each across an edge. Vertex cover is easy, but eliminating independent set is hard. So these kinds of results can also be interpreted in some other things in terms of the state space where this reconfiguration happens. So what I mean by state space is a graph where a vertex is a configuration of the tokens, some vertex cover. They are connected by an edge when one can be reached by the other. And in case of vertex cover, the implied results are that it's connected because we can reach any solution from another, and it also has small diameter because the sequence we generate is short. So for dominating set and independent set, it's necessary that the state space is disconnected because otherwise reachability wouldn't be hard. And also the connected components has to have superpolynomial diameter because otherwise it would be in MP. If it would have small diameter, then a path in the state space, which is the reconfiguration sequence, would be a certificate of reachability. And this is not possible when it's p-space complete. And probably the most interesting tool is that we can take the two existing solutions that we are given, and sort of the idea is to take the best from both and use them to compute a new solution, which is for us. Okay, so that's everything from me. Thank you for your attention.
Thank you. More questions?
Is your vertex cover algorithm possible to be improved? The running time?
Running time, probably. We didn't look at too much at like how to optimize it. So,
but there is nothing known on a lower bound on how fast this can be computed.
So our bottleneck is just computing normal matching and then computing the whole violator.
With your approach?
Yeah, so we just use it as a subroutine.
Yes. Mm-hmm. No, yeah. I understand.
Mm-hmm.
Okay. Second question. You implicitly assume that the two tokens cannot be on the same vertex.
Yeah, that's right.
If you allow this to happen, does anything change?
Nothing actually changes at all, because all the lower bounds that we use, they work even if we allow multiple tokens at the same vertex. So they are strong enough. And the upper bounds, they of course work even if we have like stronger rules. So okay. These two settings are same.
Okay.
Did you consider some other generalizations of vertex cover, like for example, fractional vertex cover? Because I have some feeling that if you consider like rational weights, then your algorithm. Well, I don't understand it that well. I mean, this is just a question. Like, if you consider some more general conditions on the set, for example, fractional vertex cover will still be maybe reduced to the integer problem, like 0 and nothing on the vertex to some rational fraction. There is of course the continuous version, which is.
Yeah, then it's a question of what would be the token. Would be some fractional token probably.
Yes, some common denominator. Number of tokens.
So that sounds interesting. I'm not sure how like the whole theorem could be used in such a case. We could do something like that.
Oh,
it probably depends on that.
Yes. Oh. Any other?
Maybe I missed it, but in all the problems, the the solution to the problem is given by the optimal one, or is it like so for example, if I take the vertex covers all vertices, the independent set is just maybe 3 vertices of the graph. It cannot be that hard, right?
Yeah, yeah. You can it can be any size on the input.
Oh.
Yeah.
And so can it happen? So for example, independent set is hard, but it seems to me that the hardness comes from the fact that like it's hard to move independent set because the vertices are independent in each step. So can it happen that, for example, if you restrict the size of the independent set to say, I don't know, half of the vertices, or maybe fraction of the vertices, then it can become beta?
It could be. It could be. That's interesting question.
Okay. So
If that is all questions, then thank you again, and thank you.